So our last speaker for this session is Jaemin Choi, who is a PhD student at PPL. He's going to talk about advances in heterogeneous computing in Changa++.
Thank you, Juan, for the introduction. So my name is Jaemin Choi. I'm currently a second-year PhD student here at the Parallel Programming Laboratory. Okay, so the title of my talk today is Recent Advances in Heterogeneous Computing using Changa++. So I just wanted to say that Michael Robson contributed some slides to this talk, so thank you, Michael. So I just want to start off with a very brief introduction to heterogeneous computing. So in general, heterogeneous computing is just computing with different types of devices. But in this talk, it will be specifically about using GPUs to boost the performance of the applications. So GPUs are throughput-oriented devices, as you all know. And it's data parallel, or SIMD. We are executing a single instruction for multiple data. And it has many simple and low-frequency cores, in contrast to CPUs, which have less number of cores and more high frequency. And GPUs also give you teraflops of computing power. And also another important aspect of GPUs is that they have a separate memory space, which are usually GDDR or HBM in hardware. And also it's very important to think about the overheads of data transfers. So now GPU devices are a critical factor of performance, also in HPC applications. So let me just first talk about how we can utilize GPUs in Changa++. So there are basically two ways you can do this. First is just using CUDA directly in your code. So you can have each char offload small kernels to the GPU. Or you can manually aggregate the data and work at a synchronization point and then offload one big kernel. And the second method is using GPU Manager, which is a library that we provide in Changa++. But what is GPU Manager and why should we use it? And that will be my next section of the talk. So there are several problems when we want to use GPUs with Changa++. And these problems are caused due to over-decomposition and asynchrony that are present in Changa++. So there are three issues that I could think of when we are using GPUs. So the first is granularity of work. Second is the blocking property of the offload API that is used to offload work to the GPU. And the last issue is the responsiveness issue. So I'll go into more detail about these in the next slides. So the first problem, which is the granularity of work, because in Changa++ each char or object is fine-grained, they contain very little data and work. So that means when we offload these chars to the GPU, that will eventually turn out to be small kernels. And an important aspect here is that the kernels, these small kernels should be able to execute concurrently on the GPU to be able to utilize the entire GPU. Otherwise, we need to aggregate these small kernels so that we can utilize the GPU. And the second problem is the blocking property of the offload API. So the commonly used APIs, CUDA APIs, to wait for GPU work to complete are the following: CUDA device synchronize and CUDA stream synchronize. And the problem is that these are blocking calls. So PEs are implemented as persistent threads on CPU cores in Changa++. And that means a blocking call to wait for GPU work will prevent other chars from executing on these cores, or PEs. And another problem is that the number of concurrent kernels that can execute on the GPU will also be limited to the number of PEs. So if we have 8 PEs, that means only 8 concurrent kernels can run on the GPU, even if we have more than 8 chars that are waiting to offload work. So the offload API should be non-blocking for Changa++. And the last issue is responsiveness. So there are two sub-issues to this problem. The first is slow initiation of GPU work. And this is caused because when a char wants to offload work, this offloading must wait if the target PE or target CPU is already being used by another char, even if the GPU is free. And the second issue is slow response. So when we have an offloaded work that is complete on the GPU, and we want to handle this completion on the CPU, but if the target CPU or the PE is busy, then that handling will have to be delayed. So in the current GPU manager, it addresses the second problem, which is the blocking property of the offload API. So what the user needs to do is he or she needs to construct and submit a work request object that specifies the data buffers and the directions of the transfer, and also the kernel that should be executed and the specifications of it, so such as the grid size and the block sizes. So after the user submits this work request, the runtime tracks these work requests that could have been submitted by multiple chars, and the runtime is able to then overlap these data transfers if they are in opposite directions, and overlap these data transfers with the kernel execution. But the problem here is that it is not able to overlap multiple kernel executions or concurrent kernel executions. And this is because only one CUDA stream is used for kernel execution in the current implementation. But the good thing is that the execution continues without blocking after the user submits work requests, which is addressing the second problem. So internally in the current GPU manager, 3 CUDA streams are used, data in, kernel, and then data out. So as I said before, the problems are that there's only a single CUDA stream that can execute kernels. And also the API that uses work request is unnecessarily complex. So I'll now talk about the new GPU manager, which will be included in the new release 6.9. So this new GPU manager partially addresses the first problem, which is the granularity of work. So the new GPU manager now allows kernels to execute in separate CUDA streams instead of just a single stream. And the runtime support for providing support for kernel aggregation in the runtime is still ongoing research. So now the user can still manually aggregate work and offload it to the GPU. And this non-blocking feature and API is implemented using the CUDA events feature. And it also has a much simpler API, which is almost identical to the CUDA API. So we call this hybrid API, which is what we've been calling this traditionally. So instead of the CUDA prefix for the API calls, we now have the happy prefix. And so the core API in this hybrid API is called happy add callback, which is able to invoke the provided charm++ callback function when the specified data transfer or kernel execution completes on the GPU. So this actually replaces the CUDA stream synchronize call that users have been traditionally using. And there's also ongoing research to address the last problem, which is the problem of responsiveness. So to talk a little bit more about the non-blocking implementation of offloading. So as I said before, we use CUDA events to detect the completion of GPU work. So to do this, each of the PEs maintain a queue of events, and each queue is checked in the scheduler before we choose what to execute next. And the charm++ callback that was provided by the user is invoked on the completion of the specified operation, whether it be a data transfer or kernel execution, and then the runtime is able to continue the flow of the program without waiting for the GPU work to complete. But the problem is using CUDA events to implement this kind of feature is impractical for the user because it's unclear where in the program flow that this event queue should be checked. And it's also unclear how frequent this checking should occur. And I also wanted to mention that there's an alternative to using CUDA events for this non-blocking feature, which is CUDA callback. But with the CUDA callback feature, there's only a single callback thread that takes care of all these invocations of the provided charm++ callback functions, and this thread becomes a bottleneck. So I just wanted to compare the complexity of code and this is just a simple matrix multiplication code. So this code is the current GPU manager code, where so the first function is the actual invocation of the kernel, and you can see that it's fairly complex. You have to specify which buffers that are stored in the runtime needs to be moved to the GPU in a pretty complex manner. And the second function is basically all the creations of the work requests and specifying which buffers should be moved and which direction they should be moved and whether they should be freed and the size of these buffers and so on. So you can see that it's pretty lengthy. And the second set of codes. So on the left, you can see the CUDA code for the same matrix multiplication invocation. You can see that it's much simpler. And on the right, we have the new API in the new GPU manager. And you can see that it's about the same complexity as the CUDA API. And you can see that instead of CUDA mem copies, they're replaced with the happy prefix. And also for other CUDA API calls. And this happy check function is just a convenience that we provide for users, that they can check if an error has occurred during data transfers or kernel execution. So to evaluate the performance of this new GPU manager, we have tested this on a single compute node of OLCF Titan, using up to 8 cores of AMD CPUs, and also using the NVIDIA's Tesla K20X GPU. So the first benchmark that we tested is Busyweight, which is a very contrived benchmark. So this is designed to validate if the new GPU manager is doing what we expect it to do. So here we have tasks or kernels on the GPU that Busyweight both on the CPU and the GPU. And here we vary how much work out of the total work is offloaded to the GPU, and also how long they take on each of the devices, either on the CPU or on the GPU. So we have 3 configurations of task configurations. So one is when the CPU is faster than the GPU, when the task runs faster on the CPU. And the second is when the task runs faster on the GPU. And the last is when the tasks run the same time on both devices. So we use APs for the 8 cores. And here we have 16 chars per PE. That means we have 128 chars total. And we run 100 iterations. So as I said before, if we do not use, even with the current GPU manager, we can only execute 8 concurrent kernels at a time. But with the new GPU manager, we can execute 32, which is the maximum for the Kepler GPU. And here we see up to about 4.8 times speed up compared to directly using CUDA, mainly because of the non-blocking features. And also, you'll be able to see it in the graph I'll show you, that the effectiveness of the runtime support depends on the characteristics of the application. So this graph is the results of the Busyweight benchmark. And you can see, so on the x-axis, we have the offload percentage, which tells us how many of the total chars are offloaded to the GPU. And on the left axis, we have the speed up. So you can see that the effectiveness of the runtime support varies greatly on the characteristics of the application. So how much work we offload to the GPU, and also how long they run either on the CPU or on the GPU. And the second benchmark that we ran is Stencil 2D. So also this is a very simple 2D 5-point Stencil benchmark. So this is to evaluate the effectiveness of the GPU manager under a more realistic workload. So we have the following grid, which is decomposed into 512 blocks or chars. So here we have 8 Ps and 128 chars per P, which means we have about 1,000 chars total. And here we also vary the percentage of chars that gets offloaded to the GPU. And again, we can run 32 kernels instead of 8 without the GPU manager. And here we see up to 2.7 times speed up compared to directly using CUDA. So this is the plot that shows the speed up. So the blue bars are using Charm++ and CUDA directly. And the red bars they show using CUDA and Charm with the runtime support. And the yellow line shows the speed up. So you can see that the runtime support is able to provide some good speed ups depending on the percentage of work that gets offloaded to the GPU. So I'll now move on to some GPU applications that use the GPU manager. So the main one is Changa, which is a cosmological n-body simulations. It was presented by Professor Quinn yesterday. So in Changa, we offload the physics kernels to the GPU. And there's also active work in optimizing these kernels so that they can run faster on the GPU. And this plot shows the recent results of Changa. And you can see that compared to the base cases, the CUDA versions, which is this red and yellow lines here, and also this blue and kind of red bar, show that they offloading work to the GPU gives us pretty good speedups. And this is the Dwarf One Benchmark running on 4 XK nodes of Blue Waters. And this is the offloading the entire tree walk to the GPU in Changa. So the top diagram shows how the tree walk has been done previously without using much of the GPU. Almost everything was done on the CPU. And the diagram on the bottom shows the work done by Jianxia Liu, who's a collaborator at Purdue University, who was able to offload much of the tree work to the GPU, providing about 4.8 times speed up over the baseline in the best case, and about 3.6 times speed up on average. And this is a plot that was provided by Mert Hidayatoglu, also here at the University of Illinois. So this is also the Dwarf One Benchmark, which was run on various types of machines. So to conclude the talk, this work on the new GPU manager was presented as a SRC poster at SC17 last year. So we've seen that there are 3 main issues using GPUs in Chang++: granularity, the blocking API, and also the responsiveness. So we've mostly resolved the second issue, but we need to do some more work on resolving issues 1 and 3. And so we've seen that there are some interesting research topics with fine-grained tasks and using GPUs. And also there's the importance of using accelerators is increasing even for regular applications, as we've seen for doing tree walks on the GPUs in Changa. So that concludes my talk. Thank you. Any questions?
Quick questions, doesn't need the microphone, but go to slide 19 and explain a couple of things for this. Why is SMP slower?
So Michael Robson is actually a good person to answer that question.
This is the known, these are older numbers. I didn't have.
Repeat the question.
So basically the question is, why is SMP mode slower here? This is a small scale problem, basically. So if we have other numbers, I didn't put them in the presentation, where SMP mode is necessary for scaling, and it's actually a lot faster. So these are old numbers. They're from a couple months ago, and I didn't have enough time to get updated ones. So I think we fixed this. But we can talk about it afterwards. So it's I think Changa at small scales for some reason does not work well with SMP. Might be because we lose a COM thread, but we haven't totally figured out why.
The CUDA version, the base CUDA version before was done by who?
That's without, there's with CUDA and without CUDA basically.
Kernel. No, go forward to slide. Yeah, this one.
This one was done by Jian Chao
Yeah.
recently,
Bottom
very
part.
recently.
What about the top part?
This is the original Charm application. That's like it's what currently exists in Changa and then his innovations of moving the tree walks to the GPUs.
Changa CUDA kernel was written by
Which CUDA kernel?
top figure, shaded boxes, square boxes. What? There is stuff running on GPU with the top figure.
Yeah. Yes. This is moving, so this graph is just showing moving building the
So-
trees from the CPU to the GPU.
Yeah, I think Sanjay's just asking who wrote these kernels. Yeah.
The
in
force
Changa.
kernel? I don't know, this is before my time.
Just wanted to make sure Tim gets credit if he wrote it. So
No,
you wrote it?
no. The old Force kernels were written by the name escapes me. I'm sorry. Yeah, this was like 2007, 2008, long time ago. But Zhongguo had to rewrite the Force kernels
Right.
in order to interact with his new tree walk system. So these new Force kernels are actually untested. I'm working on that.
Do you see any application characteristics that won't benefit from your modifications that you made to GPU Manager? Like you showed two applications, one of them showed 5x, the other was lesser than 5x. But
Right.
do you see any sort of other application characteristics which would give worse performance with this kind of updates?
Yeah, so if we go back to the results, actually this Busyweight benchmark, you can see that these parts, like when the CPU runs much slower, when the same task runs much slower on the CPU than the GPU, and also when when a relatively small number of chars are offloaded to GPU, we have very little speed up. So in cases such as these, you wouldn't see much speed up. Yep. Okay, thank you.